Okay. So we're going to move on to chapter 21 on magnetic forces and magnetic fields. And we'll start out by just assuming magnetic fields exist and talk about the effects that they have. And so basically, magnetic fields exert forces on magnetic charges, or on electric charges. And the magnitude of the force is given by this equation here. And again, this is just the magnitude of the force. So Q is a charge, V is a velocity, B is a magnetic field. Again, just put them all in as positives. We're just dealing with a magnitude. And that theta, that is the angle between the velocity vector and the magnetic field vector. So now we can talk about the magnetic force. We can calculate the magnitude of the force. Magnetic fields are measured in Tesla, and we have this unit conversion factor here. So velocity is meters per second. So if we just multiply by a second, force is a Newton, so Newton times a second, Coulomb, meters, Tesla. That's a very useful unit conversion factor. Now that just gives a magnitude of the force. Now, if theta is 0 or 180 degrees, so if you have, like, say we have a magnetic field to the right. If we have a charge moving either with the magnetic field or against it, you know, here theta is 0, here theta is 180 degrees. In both cases, sine of theta is 0. So there would be no magnetic force in either of those cases. So we can assume that if there's a magnetic force, the velocity and magnetic field vectors are not parallel to each other. And so they will define a plane. Like in this case, if we just have here, there's a lot of planes that can, you know, go through this direction. You could have the board, or you could rotate the board, and both of these vectors would still fit in that plane. But the force is 0 in that case anyways. So if they're not parallel, these two vectors uniquely define a plane. And the force is going to be perpendicular to the plane defined by velocity and magnetic field. So in order to find the direction of the force, we use the right-hand rule. So let's say that this is an electron moving in this direction. The magnetic field is in that direction. What direction is the force? Someone want to give this a try? Let's start with this. Let's say that the board is an XY plane. And so we have possible directions for the force on the electron. Say it's in the X direction. Here, let's do this. So now I guess more generally, it could be in the XY plane. Let's say let's do this. Let's just change the magnetic field like that. Okay. So possible directions for the magnetic force. X, Y, negative Y, into the board or out of the board. So does anyone want to answer this one?
Out of the board?
Okay, so you did the right-hand rule. So you put your fingers in the direction of velocity, curl towards the magnetic field, thumb points out of the board. So is that how you got that?
Yeah.
Okay. Well, you did the right-hand rule correctly, but there's one other thing involved here. This is an electron. So remember, for a negative charge, it's in the opposite direction. So yeah, you got the right-hand rule part down, but you also have to take into account the charge. So yeah, you do your fingers in direction of velocity, curl towards the magnetic field, thumb points out of the board, but because it's an electron, you have to reverse it. So it'd be into the board for a negative charge. Let's do another right-hand rule problem. Let's say we have a region like this with a magnetic field. This time, let's have a positive charge. It's going to enter this region with a magnetic field and go like that. So the question is, what direction is the magnetic field? And I'll just tell you, into the board or out of the board. There are, I could say like X or Y, but it's not any of those. Let's just stick to into the board or out of the board. So, anyone want to give one of these a try? So, I don't know what the answer is. Let's guess into the board. No, that actually works. So, it only takes one guess. But yeah, so again, let's just guess it's into the board. So if you put your fingers in the direction of the velocity, curl into the board, thumb points upwards. So that would be an upward force because it's a positive charge. And so again, that's a perfectly valid way to do it. Just guess into the board. If that doesn't work, then it's got to be out of the board. And one more thing about the right-hand rule. You can always use your right hand. It's very easy to forget to take the charge into account, like the positive or negative part into account. So one thing you could do is you could say, use your right hand for positive charges and left hand for negative charges. So it's just a preference, whichever way you like it. Okay. And again, we'll do some more right-hand rule problems. Whenever they come up. So that's the force on a moving charge. Very closely related to that is a wire. Where basically it's the same thing, just you picture a wire as just a bunch of moving charges. And find the force on all those charges. We get ILB sine of theta, where theta is the direction between the current and the magnetic field. Just draw them like that. And again, the direction of the force, again, picture the current is just positive charges moving in the direction of the current. So we'd use the right-hand rule again. Put your fingers in direction of the current, curl towards the magnetic field. So in this case, the force on this wire would be out of the board. All right, so that's forces on moving charges, or currents, which are a bunch of moving charges. But a very important example of that, we noticed that we had this charge enters a region with a magnetic field. And so there was an upward force on the charge. Right when it enters the magnetic field, there was an upward force. However, so the particle is going to be deflected. It was moving straight. Now it's going to be deflected, so it's going to take a path like this. And now if it's over here, the force is no longer upwards, because the force is always perpendicular to the velocity. So now the force would be in this direction. So that's gonna affect the motion of the path. But fortunately, this is a case that we know well from mechanics, that when the force is always perpendicular to the velocity, and we know we're moving at a constant speed, because the force and velocity are perpendicular, the magnetic field does not do any work on this charge. And so if there's no work being done on it, we're ignoring any like gravity or any other forces. All right, so from the work energy theorem, if there's no work being done on it, its kinetic energy is constant. So this object will move at a constant velocity. And when the force and velocity are always perpendicular, this is circular motion. And so we know for problems like this, when you have a charged particle enter a region with a perpendicular magnetic field, it'll go through a uniform circular motion. And in that case, the acceleration is v squared over r. And this might be something worth writing down on your equation sheet. Let's just start with F equals ma. Now, the force is QVB sine of theta, or just QVB. The magnetic field in this case is, perpendicular to the board. So the velocity and magnetic field are always going to be perpendicular to each other. So theta is always 90 degrees. Sine of 90 is 1. And then we know the acceleration is v squared over r. So we can simplify this a little bit, cross off one velocity, and we can say that QBR equals mv for the circular motion type problem. Again, you don't need to write that. I didn't put that on the equation sheet, but if you want to write that down, just be clear what that equation is actually for. It only applies to this type of problem. And again, it's not essential to even write it down, because just F equals ma, like plug in force and acceleration and do a small amount of algebra to get there. So you could just figure out when you need it, but maybe not a bad idea to write it down. Yeah. Exams are coming, so why not? Okay, let's see if we can find, the kind of classic example of this is the mass spectrometer. So again, the mass of the particle, it's going to go through this curve, like this circular arc, but the radius of that arc is going to depend on the mass of the particle. If you have a more massive particle, it'll have more inertia. It's harder to change a direction of motion. So if you have, say, send two different types of particles that have the same charge, they have the same velocity, but different masses, they're gonna, move through different circular arcs, where this would be the more massive particle. The greater the mass, the harder it is. That it has inertia, wants to just keep going in the direction it's going. So if it has more mass, harder to change that direction. They'll have the same force acting on them. They have the same velocity. So here we have a smaller mass, smaller radius of curvature. And so again, if you have an element and you accelerate it through a potential difference, have it enter this region with a magnetic field, and measure the radius of curvature, I think we use the example of neon in class. That's what was in the book. And actually, you would get like 3 arcs in that case for neon. Actually, I'll put one in the middle. So with neon, you would get a picture that looked more like that. And that's because there were 3 isotopes of neon. So they have the same charge, just slightly different masses because they have different numbers of neutrons. And so you can tell like how many isotopes there are in your sample. And you can also determine, again, like the smallest one is the most common. So you can picture these are ionized particles. So you can picture these as actual currents. And I think one way you can do it, an old-fashioned way anyways, is put a photographic plate here, and you'd get like 3 marks on the plate, like one where each beam hit. But the more particles it hit, I mean, the more like saturated that region would be. So like looking at the intensities, you could tell like this one would be a lot darker because more particles are hitting it. And you can kind of get an idea of what fraction of the particles each isotope has. So a very, very useful device. So I'm trying to think, we started at 9:40. Got about 7 minutes left to cover chapter 21. I want to stick to 20 minutes per chapter. So I don't know if we want to do a problem with that or, yeah, we've got another big topic, and that's magnetic torque, also in chapter 21. So we have a force on a wire. So if you make like a rectangular wire, which you wouldn't really do, but it's easier for a purpose of calculation to consider a rectangle. And say this is in a magnetic field. So there's going to be a force on these wires, and that can cause rotation. We can cause this coil to rotate. So there'll be a torque on this coil. And we can express the torque in a couple pieces. First, we define the magnetic moment. Where the magnetic moment is NIA. So N is the number of loops. So if we just have a single wire, you know, we'd have a certain torque, but if you kind of wrap it around twice, we'd have twice as much torque. We'd have that torque applied to each coil. And A is the area of the coil. I is the current. So that's the magnitude of the magnetic moment. And then the torque, the magnitude of the torque is a magnetic moment times a magnetic field times sine of theta. So we have to talk about what theta is. Now, magnetic moment is actually a vector. Let's go back to circular coils. Much easier to make and typically that's what we come across. Like if you have a cylinder, just wrap a wire around it as many times as you want. So say we have a coil like this. We can find the magnitude of the magnetic moment, depending on, you know, in this case, A would just be pi r squared. So if we know the current and the radius, we can, and the number of loops, we can find the magnitude of the magnetic moment, but it also has a direction. And the magnetic moment is perpendicular to the coil. And the direction is given by the right-hand rule, a second right-hand rule. So what you do is you curl your fingers in the direction of the current, thumb points out of the board. Remember, we use a dot for out of the board. So the magnetic moment would be out of the board. So magnetic moment has a direction, magnetic field has a direction, and so that theta in the torque equation, that's the angle between the magnetic moment and the magnetic field. So let's say we have a coil that's free to rotate. Say the magnetic moment is in this direction, and the magnetic field is in that direction. Theta would be the angle between them. And so now we can calculate the magnitude of the torque. Magnitude of the magnetic moment, magnitude of the magnetic field, and now we know the angle. Now torque also has a direction, and what it would want to do is rotate the coil so that the magnetic moment lines up with the magnetic field. So it causes a clockwise rotation in this case. And again, a very important application of magnetic torque is a motor, where you can use a current to cause rotational motion, which nowadays you can even use to move cars. They have electric cars now based on this. Now, of course, you wouldn't use like a simple coil like this. The electric motor would be engineered for much more efficiency than this. We talked about a very simple motor, but if you just have this coil and you have a current running through, it would be like coming out of the board here, going into the board there. And so if you just run a coil current through and apply it to magnetic field, it's going to rotate the coil till they line up, and the torque at that point would be zero, but momentum would carry it past, and now it's going to be slowing down. So the torque is going to be opposing the rotation. So if you release this, it'll just oscillate back and forth for a while before eventually settling in where it lines up with the magnetic field. So not very useful, but what we would actually do to make a better motor, or to make an actual motor, is every time the magnetic moment lines up with the magnetic field, you would flip the magnetic moment. So you would change the direction of the current. That would flip the magnetic moment, and then it would rotate through again. And every time it lines up, you just flip it around. And we have one of these in lab where you can actually show it. We use this the springs to create contact. So like the current's always being fed on the same side of the coil. So it kind of automatically flip it around. But this wouldn't be a very good motor because the torque would vary a lot through its motion. So it's momentum that keeps it moving, but it would be speeding up and slowing down as it goes through. So of course, engineering, you can create much better designs, or they're much more consistent torque and things like that. We're just focusing on the basic idea though. Okay, so that's chapter 20. And actually, that's not quite chapter 20. We also have Ampere's law, which is this kind of strange looking one, but let me write it down. So yeah, Ampere's law can actually help us calculate magnetic fields, at least in some cases. So what's on the left side of this equation looks fairly complicated, but say you have a loop. And there's a magnetic field in the region. And so what we do is let's look at, like, say, this part of the loop right here. That has a length delta L. And the magnetic field at this point would look like this. And so we look at the component of the magnetic field in the direction of that line segment. Call that B parallel. And then if you multiply by the length of the line segment, you get B parallel delta L. And that's just for that one line segment. So what you do is you have to break your loop into pieces and calculate B parallel delta L over every piece and add them up. And really, this process where you break things up into pieces and add them up, that's called integration. That is a problem that we do in a calculus-based class. So we can't really do that, which is why we have this awkward notation. We can write it a little better with calculus. But yeah, that left side, we go through that process. And the right side is the current that is passing through this. So like we have a closed loop. So there's like an inner surface and there's like an inside and an outside, basically. And that I enclosed is the current passing through the surface. And current can go in either direction. So it can go like into the board or out of the board. And again, you can like pick a direction. Like let's say into the board is positive. So if into the board is our positive direction, then this case B parallel delta L would be positive. So into the board, that'd be like a clockwise rotation using the right-hand rule. So here, because the magnetic field is going in this clockwise direction, that term would be positive. But over here, you're tracing this clockwise. So here you have a magnetic field going to the right, but delta L is going to the left. So for like this segment here, B parallel delta L would be negative. So these terms here could be either positive or negative. And then a current going into the board would be positive. So if you had a current coming out of the board, that would be like, for I enclosed, that would be negative if we picked like into the board as our positive direction. So if you have multiple currents going in different directions, like say you have 3 amps here, say coming out of the board, 2 amps going into the board. Into the board is what you picked as your positive direction. Then in this case, I enclosed would be minus 1 amp. Or you can pick the other direction. Picking the other direction, it's basically just like taking that whole equation and multiplying by -1. So it doesn't matter what direction you pick. That'll give you the direction for both the current and the sign of each of these terms. So if you just switch the other direction, both of those will be reversed and they cancel each other out. The negative signs do. So Ampere's law can be used in a couple of cases to actually find the magnetic field. One of those cases is a long straight wire. And the other is a solenoid. Where here, N is the turns density. So it's like the number of loops in the solenoid divided by the length of the solenoid. U naught, of course, is our constant, and I is the current. And solenoids are great for creating constant magnetic fields. So if you have an actual solenoid, in practice, magnetic field might look like this. Well, magnetic field lines can never cross. That was just a bad drawing. But then you can get these. So a real solenoid might look something like this. But if you stay away from the edges and just look at the interior of the solenoid, you basically have a constant magnetic field, which is just along the axis of the solenoid. When you get near the edges, it spreads out a little bit, but otherwise, that's it. It's a way to create a relatively constant magnetic field. All right, so any questions on chapter 21? All right, let's go to 22, which is on Faraday's law and induction. Let's get rid of this. So we define magnetic flux, same way we define electric flux. And here write down Faraday's law. Here, just to distinguish it. Faraday's law says that the EMF, or electromotive force, is minus, which we usually ignore that minus sign, but it is the rate of change of magnetic flux with time. So in order to have flux, we need a surface. So if we have a surface, it could be anything basically. So let's say we have a surface. If there's a magnetic field, let's make a more reasonable surface. Let's say a circle. So, or we have a flat surface, say the boundary of that surface is a circle. And so we can calculate the flux through the surface, and the EMF, that is the EMF around the boundary of that surface. And that only occur that EMF is caused by a change in flux through the surface. So let's say at T equals 0. Let's say this is a conducting loop. It's like an actual wire. So let's say at T equals 0, it looks like that. And then sometime later, let's say there's a magnetic field. So there's definitely a change of flux here. Initially, the flux was 0. At some later time, we have a flux now because there's a magnetic field passing through this surface. And so there will be an EMF around the loop while that flux is changing. And that minus sign gives us the direction of the EMF. But for our purposes, usually what we do, in cases where this minus sign would matter, we don't really use that. We use a different thing called Lenz's law, where, yeah, let's just say that this, yeah, so that earlier this is a conducting wire. So this EMF will drive a current. And we want to know what direction the current is going to be. So is the current going to be clockwise or counterclockwise? And so, again, you could do that just with Faraday's law and that minus sign, but it's often easier to just use Lenz's law. So what we do is first we look at what is delta phi, the change in flux. That would be out of the board. So we had a flux of 0, the final flux is out of the board. The change was out of the board. And so that changing flux creates an EMF. And because the it's a conductor, that EMF will drive a current. And now Lenz's law, and so if we have a current now in this wire, that current will create its own magnetic field, which will, the induced current will create a flux through this loop as well, because currents create magnetic fields. And so what Lenz's law says is that the induced current will create a flux to oppose the change in what created the induced current in the first place. So if the change in flux is out of the board, then you put your thumb into the board. This would be a clockwise current. So the induced current would be clockwise. If you look at a clockwise current, if you just look at, say, this piece here, remember from the right-hand rule, you put your thumb in the direction of the current. Like say you have a wire. We know magnetic field lines form these closed loops around the wire. And to find the direction, we have the right-hand rule. Put your thumb in the direction of the current and your fingers curl around in the direction of the magnetic field. So if you put your thumb in this direction, magnetic field's into the board. Put your thumb here into the board. Hard to do it this way, but also into the board. So it's easier just put your thumb into the board, the opposite direction of delta phi, and that'll give you the right direction for the current. So to find the direction of the induced current, you have to get this part right first. What direction is delta phi? And that's not always entirely trivial. And then pick the right direction for the induced current to oppose that change. So if delta phi is out of the board, put your thumb into the board, that'd be a clockwise current. Let's do one more Lenz's law problem. What if we had a situation like this? We want to know the direction of the induced current while this magnetic field is changing. And again, want to look at delta phi. Now, at both the start and the end, the flux is out of the board, but the flux is weakening. And so the change in flux would be into the board. So the change in flux is into the board. So the induced current would then be counterclockwise. So remember, opposite. You want to oppose the change. So if the change in flux is into the board, you want to go out of the board, that would be a counterclockwise current in this case. So even though the initial and final flux are both out of the board, the change in flux is into the board in this case. All right. One more thing about Faraday's law. The flux consists of the magnetic field, the area, and the orientation, like the angle between the magnetic field and that perpendicular direction. So like we have our surface here, it has an area where we draw a normal line, and that theta is the angle between the normal and the magnetic field. So there's three things that determine the flux: the magnetic field, the area, and the angle. And so if you change any one of those, you will get an EMF. So again, if you have a constant magnetic field, if you were to rotate this loop, that would create a flux. That's a very important example of flux because that's how we produce most of our energy. So you mechanically rotate this, this coil, and that'll create an EMF, which will drive a current. So this is kind of the opposite of the electric motor, where you're causing a rotation, or you're using a current to cause a rotation. In this case, you're using a rotation to create a current. So kind of the opposite of the electric motor here. So this is how we generate energy. So we mechanically rotate this coil, and that'll create, the EMF will be constantly changing because the angle's constantly changing. And because it can be increasing or decreasing, we would get the This is what we call alternating current. Okay. But another way you can do it, let's say you have an actual coil here. Say you just push on it and you turn it into this. So it's the same length of wire. It's the same magnetic field, but the flux would change in this case. So you would have an induced current in that case as well. So yeah, anything changes a flux, that'll produce an induced current. And a generator is a very important example of that, where the EMF would be described by a sine function. So if you rotate the coil with an angular frequency omega, sine function, or the EMF would be described by a sine function. And again, that's what you get in your outlet. You have alternating current. You have a peak current of about 170 volts, and that's oscillating up and down. All right, now let's talk about induction then. So if we have, say, a simple circuit with a switch and a resistor. So we have a battery, a switch, and a resistor. And let's say we flip the switch, we know we'll get a current in that case. So we flip the switch. So initially we had no current. And now before, we close the switch and we say, just from the loop rule, that, well, we could do this. Just using the loop rule, epsilon minus IR equals 0. Just using our loop rule. But it's not quite that simple now, because once we close a switch, we have a changing current. So the current was initially 0. We know that after we close the switch, we're going to have a current. And so there will be a change in flux in this loop itself. So we're applying this loop here. But now, while the current is changing, while it's going from 0 to its maximum current, there's going to be a magnetic field building up. We will be creating a magnetic flux into the board. So we'll create a clockwise current. That'll create a magnetic flux into the board. And so there is a changing flux. So we can apply Faraday's law and say that EMF due to the battery minus the so if we take Faraday's law into account, we have this additional term due to the changing flux in the wire. And so, like I said before, deal with like steady currents, but things get more complicated when the current is changing. So that's that complication. Now, this would be a very difficult thing to calculate because the flux, calculating the flux in the surface for a given current would probably be difficult because it's not constant. It depends on we treat it as 4 wires if they form a nice rectangle. But so the actual magnetic field would be different at different places. So we'd have to do a lot of calculations to find the magnetic field inside and then see how quickly the flux is changing. And so usually we don't actually do that calculation. We can define for this circuit something called the self-inductance. And which will depend on how quickly the current is changing. So we call self-inductance L. It's measured in henries. and it depends on how quickly the current is changing. So actually calculating L for this circuit would be a pretty difficult thing to do. We're obviously not going to do that, but it is there. So again, it could be done, but we're not going to do it. All right, so that's called self-inductance. And now in a circuit like this, L would essentially be 0. And again, if we had an actual lab to work with, you know, it'd be very easy to show that. You could, you have a voltmeter. So you actually hook up the circuit. And when the switch is open, the voltage would read 0. You close the switch, and the voltage would read or let's put an ammeter in here. So yeah, as soon as you flip the switch, it might take the meter small time to actually adjust itself, but you'd see the current go to the EMF of the battery divided by the resistance. It would just look like this, basically. It would be an almost instantaneous change. So inductance and something like this is a very small term, but we could create a device that would have significant inductance, and that would be putting a solenoid in the circuit. And the reason that solenoid would have a significant effect, we know magnetic field is parallel to the axis of the solenoid. That would give us maximum flux through each loop, and you can have a lot of loops. So if you have an inductor, that would introduce a certain amount of inductance into the circuit. So again, the current couldn't go from 0 to its maximum value nearly instantaneously. What that inductor would do is it would make that rise much more gradual. And again, this is still what we call a direct current, because we just have a battery providing a constant voltage. Things can get very interesting if you were to plug something like this into an outlet, because there the current's constantly changing. Remember, inductance acts kind of like inertia. It resists changes in currents. So if you try to rapidly change the current, you'll get a very large back EMF to oppose that. And so inductance has a very significant effect in alternating currents. Yeah, direct currents, it just lengthens the scale there. But for alternating current, you can get some rather interesting results. But again, really to get into this in any detail requires calculus, so we don't do too much with it. But now let's look at another system. Say we have let's say this. We have a battery just like before, but now let's say we put another coil next to it. So we have like coil 1, or this one is hooked up to a power supply. Let's call this the primary coil. And we have a secondary coil, which is not hooked up to a power supply. Now, if we flip the switch here, that'll create a current in the first coil, which will create a magnetic field, which the magnetic field extends beyond the coil itself. So flipping the switch here will create a magnetic flux over here. Probably not a big one, because it would depend on geometry, like how close these coils are, but there will be some flux here. And so initially, before you had a current in the primary coil, the flux was obviously 0 because there's no magnetic field. So when you flip a switch here, that'll create a magnetic flux here, which will drive a current in the secondary coil. And so we call this mutual induction. We have two separate coils, but they're connected because they're just by proximity. A change in one coil will, in the current in one coil will create an EMF in the, I don't know why I call this coil, it could be secondary coil. Okay, so changing the current in the primary coil will create an EMF in the secondary coil. And again, the more rapidly you change the current in the primary coil, the greater EMF there will be in the secondary coil. And they are related by, we call that the mutual induction, also measured in henries. And a very important example of that is the transformer, where you have like an iron donut, basically, to guide the magnetic field lines. Because normally mutual induction might be small. If we have a situation like this, there'll be a magnetic field created all around this coil, and only a small portion of it is going to go through the secondary coil. So the mutual induction would be rather low. We're not going to get too much of an effect in the secondary coil. But if we use, like, iron can guide magnetic fields, so if we have a primary coil and a secondary coil and connect them with a donut, so like say here's our primary coil. Let's say we plug this into an outlet. So we have alternating current. So again, it's basically like a solenoid wrapped around this donut, but because of the magnetic field, it'll wrap the magnetic field lines very efficiently around here. So if we put a secondary coil over here, say hook this up to some device, which will have an internal resistance, we can basically say in this case that the flux through each coil is the same. Now, that's not 100% accurate, but basically the magnetic field lines are going to pass through every coil. Some of it's going to leak out, but to a fairly good approximation, we'll get the same flux through every coil. But we have a different number of coils. And so this ratio, say the number of coils, or the number of loops in the primary coil divided by the number of loops in the secondary coil, that's equal to the ratio of the EMF. So here we have the EMF in the primary coil. Here we'd have EMF, which you drive a current in the secondary coil. And there's an inverse relation when we look at the currents. And again, this is an approximation, but that last equation, that's a result of the power. We're assuming a perfect transformer with no loss of energy. So we have a current in the primary coil and a current in the secondary coil. And so let's say this is a step-down transformer. So if we have 120 volts, a step-down transformer would lower the voltage. Let's say we lower it to 40 volts. Then our power is current times voltage. So the product of the primary EMF and the primary current has to be the same as the secondary EMF and the secondary current. So if we lower the voltage, we have to increase the current by the same factor. So that's why there's that inverse relation. If you just cross multiply here, EMF in the primary times the current in the primary would equal EMF in the secondary times the current in the secondary. And so this transformer is a very, very useful device. You probably see these all the time. Like when you plug something in that is that little box, that's the transformer's in that box. So you plug that into the outlet, which is a standard 120, at least in America. Different countries have their own standards, usually like 220 or something in England or Europe. But yeah, so the device that you're plugging into the outlet might have its own needs. You don't want 120 volts there. So it would have a, say, step down transformer that'll lower the voltage, whatever the device needs. So a transformer, that's an extremely important device. You can have just a standard outlet and plug anything into it by building the transformer for that device. And another use for a transformer, another very important use, is in power transmission. So again, think of how far the closest, like where your house gets energy, that comes from a power plant, which is somewhere, you don't know, probably miles away. And these power lines carry a lot of energy and over a large distance as well. So normally we look at the wires we deal with in lab, we ignore any like energy lost in the wires. But for power transmission, we're dealing with huge currents and long distances. That could be a significant loss of energy in the form of heating, which is undesirable. And it turns out transmitting power at a high voltage is more efficient than at a lower voltage. And so there's like a sequence of transformers in our power grid. So we create power at the power plant, and then there's a step up transformer, which massively increases the voltage, which will decrease the current. So the small current, we can transmit energy very efficiently, but it's at an extremely high voltage, which is dangerous, which is why we, those lines you see on the side of the road, they're separated. Well, they're up high, so you can't go near them because that would be very dangerous. And they're also separated. You don't want like if a bird was able to touch, like land on the wire and touch both wires, that could totally fry the bird and maybe short circuit the power supply as well. So yeah, anyways, it's a dangerous situation, but efficient. And so then when it gets into your neighborhood, there'll be a step down transformer, which lowers it. And then that branches out to different areas. And then there'll be like another one before it goes to your house. And so you typically have 120 volts delivered to your house. Now our actual power grid is a little bit more difficult than that. I can use like 3 lines that are all out of phase with respect to each other. And by combining them in different ways, you can get 120 volts or 240. So you might have some outlets in your house that are actually at 240 volts. That would be for like big appliances, like washing machines or something. They might require a higher voltage. But yeah, so transformers, very, very important. And these rely on induction. You can't get this kind of easy way to change voltages with direct currents. So that's why we use alternating current. Well, that's how we generate power, but also how we can make it much more useful by changing the voltages with a relatively simple device. All right, so we're kind of out of time, but we do have one more chapter on electromagnetic waves. Kind of just summarize electromagnetic waves. So we have electric and magnetic fields, and well, an electromagnetic wave we have alternating electric and magnetic fields. So remember in Ampere's law, now, guy named Maxwell actually discovered in two different ways that there was a problem with Ampere's law. One mathematical and one based on physics. He knew there was something wrong with this. And he wound up correcting this equation. There's something missing from this equation that Maxwell corrected. So we had Faraday's law, where say we have a changing magnetic field, we said like that'll, or say we have a changing magnetic flux. That'll drive a current in a conducting loop, but more generally, that'll create an electric field. So if you have a changing flux here, that creates an electric field. So you can think of Faraday's law, changing magnetic fields can create electric fields. And what Maxwell discovered is that changing electric fields can create magnetic fields as well. And basically we get, Maxwell discovered this concept of an electromagnetic wave, where if you have a changing electric field that creates a changing magnetic field, and that changing magnetic field creates a changing electric field, they can like feed off of each other and create a traveling electromagnetic wave. And so if you were to take a picture of a wave, it might look like this. Like the electric field would be a sine wave. So this would just be like at one moment in time, the electric field, it's changing. And again, this would just be like a snapshot. So, the whole wave is moving to the right. But right now, the electric field would look like this. And the magnetic field is perpendicular to this. See if I can draw this. It's hard to draw because the magnetic field comes out of the board. I think I have to draw it like this. It is hard to draw, but we can find better pictures, like in the book. But the electric and magnetic fields are perpendicular to each other. And they're perpendicular to the direction of the wave. And the orientation is given by the right-hand rule. So if you put your fingers in the direction of the electric field, curl towards the magnetic field, your thumb points in the direction that the wave is moving. And the magnitudes are also related by the speed of light. So Maxwell discovered, when he came up with the idea of an electromagnetic wave, he found he could calculate the speed of the wave. And when he did that, he found it was the speed of light, which was a really, really amazing thing. So he said that light is an electromagnetic wave, and that was quickly confirmed experimentally. Okay, so the electric and magnetic fields are perpendicular to each other. The magnitudes are related by the speed of light. And we can, this is like a picture of the wave. You go from like, say, one peak to the next. That would give us the wavelength. And the wavelength and frequency, this is a very important equation. In general, for any wave, the frequency and wavelength are equal to the speed of the wave. So for light, frequency times wavelength is the speed of light. So if you know the frequency, you know the wavelength, and vice versa. Now, for visible light, typically around 400 to 700 nanometers is visible light. Now, so again, you look at the frequency range for that. It's somewhere around 10 to the 14 power hertz. So these waves are oscillating extremely rapidly for electromagnetic waves. And again, it goes, visible light is an electromagnetic wave, but the spectrum goes way beyond that. We have and for extreme long wavelength, we have radio waves. And then as we decrease the wavelength, we have like microwaves and like infrared, then visible, starting at red with the longest wavelength, down to violet or purple is the lowest wavelength. Then we have ultraviolet as the wavelength gets even shorter. And then we can go down to like X-rays and gamma rays, which are extremely short wavelengths. So there's this whole electromagnetic spectrum. They're all electromagnetic waves. The only difference is the wavelength and frequency. There's nothing special about light. That's just what we can see. But you know, the stuff we can't see is just as real as what we can. Although I will say that this picture that light is an electromagnetic wave, that did not last too long, at least as some kind of absolute picture of how light works, because I think it was, you know, within 10 years or so. Well, maybe closer to 30 years. If you look at when Maxwell did his thing, I think that was 1879. But then there was some time before they could confirm this experimentally. But maybe 20 years later. So they just got this very solid idea of light as an electromagnetic wave. But then in 1905, Einstein came along and said it's not quite that simple. Light, there are certain things that you cannot explain by treating light as a wave, but you can explain by treating light as a particle. And so there's this thing called the wave-particle duality, where light can behave as a particle and a wave. And interestingly enough, it's not just light. Particles actually behave like waves as well. You just don't see it very often because it depends on the size of the particle. But if you have extremely small particles, they can start to exhibit wave-like behavior. So we talked about in the last chapter, the double slit experiment where you shine light and you get that diffraction pattern. That's a property of waves. The same thing, you can design an experiment that will do the same thing with electrons. So you send a beam of electrons and you get that same diffraction pattern. So even things like electrons behave as waves. So yeah, everything kind of follows the same rules, but yeah, typically for ordinary matter, they have to be very, very small before you have to start considering the wave-like properties of them. Just two more things we'll talk about, but a little over time. Polarization. So again, we can describe a light, like a ray of light, with just its electric field. Because if you know the electric field, you know the magnetic field, the magnitude and direction. So again, the electric field, curl your fingers in the direction of the magnetic field, and that always points in the direction of the velocity. So like, you know, different parts of the wave, that relation always holds up. And yeah, we can describe a ray of light just with its electric field, which if you're looking at, say, the light beam is coming towards you or away from you, electric field can be oriented in a particular direction. And ordinary light is typically random. So you could have one ray that looks like this, and another one that looks like this. And for another one, the electric field will look like this. And overall, ordinary light, you'd have a huge number of rays coming at you. And yeah, there'd be so many, it would be very random behavior. It's like each have their own direction, but overall there's no preference for one direction over another. We call that unpolarized light, where if the light like this here, if we have light where all the rays are lined up like this is polarized light. where the electric field is always in the same direction. And there's various ways of creating polarized light. One of them is shining through a polarizing sheet, which due to the way the molecules are arranged in the sheet, and allows electric fields to pass through in one particular direction. So if we have a polarizing sheet, if we shine unpolarized light through it, so intensity is power over area. I don't remember in the equation sheet if I use S or I. So maybe it's I. I should check. I don't know where to put it. So let me check what I did in the equation sheet under like polarization. I used S, just like here. Okay. So S is the intensity of the beam. That's a power over the area. So if you shine just completely random light through a polarizer, that only lets light go through in particular directions. So if you have light in this direction, and it only lets the electric field go through like in this direction, this component of the electric field is going, we can break this electric field into components. That one's going to get killed off. This one makes it through. And so it's going to be reduced in intensity though, because the electric field is going to be smaller. So the light is going to be weaker. And if you have completely random light, you shine it through a polarizer, the intensity is going to be reduced by a factor of 2. So if you have like 100 watts per meter squared, shine it through a polarizer, you get 50 watts per meter squared. But now the light that comes out is polarized in a particular direction, like whatever that first sheet let through. So if you shine that light through another sheet, so let's say this is a polarizing sheet. So first one, you know your electric field is going to be in this direction. So all the light that passes through the first sheet, the electric field is going to be in that direction. And then if your characteristic direction for the next polarizing sheet, there will be an angle between it. What you get in this case you're going to be, the light or the intensity is going to be reduced by a factor of cosine squared. I say it's reduced because cosine is typically less than 1. So when you square it, it's going to be less than 1. So the intensity will be reduced. Unless that second sheet lines up perfectly with the first, in which case cosine is just going to be 1. So the intensity will not be affected, but typically it'll be reduced. So we have 2 rules for light. Unpolarized light. This is for light that's already polarized going through a second polarizing sheet. And one more topic in this section, that is the Doppler effect. Where if the source and observer are moving relative to each other, the frequency that you observe from the light will differ from the source by this factor here. You take this ratio of the speed of the speed that the source and observer are approaching or receding from each other, and divide that by the speed of light. So that's the factor that it will be affected by. And if the objects are getting closer together, the frequency observed will increase. So you use a plus sign there. If they're getting farther apart, the observed frequency will decrease. You use a minus sign. And again, the Doppler effect with light is more complicated overall than this. But if you just have an object like, say, moving in a straight line, somewhat, less than the speed of light, fairly simple formula, actually. You just need to know if you're approaching or receding from the source. And that was the last topic in chapter 24. So are there any Yeah, went a little over time, but are there any questions on anything? All right, so I'm going to stop recording so I can get to processing this.